right, can you guys hear me?
Yeah.
Okay.
Yeah.
Gabby, you sound so enthusiastic with that. All right, so thermodynamics. It's the science of relationships between heat and other forms of energy. Thermochemistry is the study of the amount of heat absorbed or given off in a chemical reaction. A lot of the first few slides. Oh, it's me. I'm hearing them on there, so there's feedback. All right. Okay. So.
You might just need to mute that for a second.
I have to. Hold on. All right. I adore you too, but you're going on mute.
Okay.
Oh, but only they can unmute themselves. Okay, is that better? Yes. Okay. All right, here we go. So, energy is anything that has the capacity to do work. Work is a force acting over a distance. Heat is the flow of energy caused by a difference in temperature. And you can think of energy as something an object can possess. And you can think of heat and work as the two different ways that an object can exchange energy with other objects. It is often misconstrued that temperature is heat. Temperature is a measurement of heat. It measures the heat transfer. Okay? So that's often misconstrued. Heat always flows from the hotter object to the colder object. Okay? You can lose heat, and the surrounding area can actually gain the heat as well, but it's going to be a flow of energy from one to the other. And it most always results in equilibrium, where the temperatures start to equal out and balance out. So going back to basic physics, sorry guys, you've got two types of energy, kinetic and potential. Kinetic energy is motion energy, potential energy is the stored energy. And in case you forgot, roller coasters. That's why the first hill of a roller coaster is always the tallest, because you have to have the most potential energy, and all that energy theoretically then takes you through the rest of the roller coaster without having to restart at a high hill. And basically wherever you start with your potential energy is where you end up with your highest amount of kinetic energy at one point, which is normally going through a loop or something.
So basically, the higher the potential energy, the more kinetic energy you get.
Yes, it equals out in the system. So if you're jumping off of a building, your potential energy is calculated by the height, the gravitational acceleration, and your mass.
And the amount of splat you hit the ground.
Well, that's what your potential energy is, determines how much splat you make hitting the ground. So the more mass you have, the bigger the splat you're going to make. So, but then if you have a person of less mass from a taller building, they might make the same splat as a person with more mass at a lower building. Really, that was disturbing. Okay.
Doesn't everything fall at the same speed?
Yes, but the potential energy that you're falling with it. The rate at which you're falling is the same.
Okay.
But the impact when you hit the ground with that force is all going to be different depending on your mass and the height at which you fall. Because of that potential energy turning into that moment before you hit the ground, when you stop moving, that is your maximum kinetic energy. No, I'm right? Okay. That is your maximum kinetic energy right there, right before you hit the ground. So once you hit the ground, now you're all potential energy again. Because you're
That's basically it. Trust me, it was confusing, but
Thank you.
Trust me, I've
Okay.
tried it.
I've done it, okay?
The concussion is finally wearing off. I'm so excited. Okay. So what are the forms of energy? And I worked at a school where this was the science curriculum. And we had to go through all the different forms of energy. And what for chemistry, really what we're going to go into is that matter and energy are interchangeable. So that as you approach the speed of light, matter can become energy. And as you slow down the speed of light, energy becomes matter or mass. So the closer you get to the speed of light, the heavier you actually get. But it's an interchange. It's very fascinating. That's all E equals mc squared. I think I said that. But all right. So electrical energy is the movement of charged particles. Mechanical energy is directly involved in moving matter. Thermal energy is heat. And chemical energy is stored in bonds, released in chemical reactions, When you break bonds, you're going from potential energy stored within the bond to kinetic energy, where it's then rearranging the atoms. Think of the ionic bonds, last chapter. I know you really hated that chapter, but think of the ionic bonds. When you put them in an aqueous solution, what happens to them? If you put salt in water, what happens to the sodium and the chloride ions? They start to move around, they dissolve, they start to break apart. They had potential energy as the solid particles. You put them in a reaction, and suddenly now they have kinetic energy and they're moving around. There is an energy, and that energy is a chemical energy, then being transferred to an electrical energy if you have that light bulb attached to it. And would be great if we could have chemical energy and then being transferred to electrical energy. But the problem is that you have to harness all of that energy, and sometimes there's not enough energy in one reaction. And the size of the quantity that you're going to need for that type of chemical reaction does not outweigh the minimal amount of energy that you're going to get out of it. Okay. We also have, if you've ever used those packets that you put in your shoes or your gloves, okay, that's chemical energy potential. You break it apart, go into thermal energy. So chemical energy is the start for many different processes that we use on the daily basis. Okay. So what is the law of the conservation of energy? It's similar to the law of the conservation of mass. Energy cannot be created or destroyed. It has to be transformed. Going back to the roller coaster and potential and kinetic energy, it has to go however or whatever the amount of potential energy is here. That's the amount of kinetic energy that you have to have at the maximum. You're not going to have any more or any less of the system. The total energy of the system is the potential plus the kinetic energy. That's all there is to it. And if you're transferring energy from one form to another, you can't exceed the amount that you're starting with. If your chemical reaction only outputs a certain amount of energy, you're not going to get any more energy out. Okay? That's why that's the solar panels, the wind energy, all the new types of renewable energy that they've come up with. That's the key. You need to find a way so that the energy going in equals the energy going out. So that way you're not wasting energy or losing energy to other sources. Like, so for example, what's the thing I'm thinking of? We do it for electrochemical cells when we do basically thermal electrical energy. Okay, some of the energy in that chemical reaction goes out as thermal energy. Well, if there's more thermal energy than electrical energy, it's not worth it to use for electrical energy. You're wasting too much in the thermal component of it coming out, right? All right. What do we use to measure energy? We use the SI unit of the joule. And the joule is defined as the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. We also use the calorie. It's a non-SI unit commonly used by chemists. It's defined as, and this is the important unit that we're going to use in calorimetry, which is this unit. It's defined as the amount of energy required, to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is equal to 4.184 joules. Now, some of you may be thinking in your head, oh, our food has calories. It does. But the food calorie is known as a kilocalorie. So it's 1,000 little calories or 4,184 joules. And yes, some of you may have had a lucky science teacher where you did the calorimetry of like a cheese curl or a Dorito or something. And you can actually measure how many kilocalories are in that. I've never done it myself. I've wanted to, but I don't. The bag ends up getting eaten. Okay, good. And I think you do get these units too, the calories, kilocalories, and the joules. All right, so the system and the surroundings. And when you're doing the calorimetry lab, which is our final lab, it's lab 12, there we go. Okay, you have the system and the surroundings. This is your system, what's going on inside. The surroundings are anything in the vicinity from which the system can exchange energy. And so this is one of those concepts that you have to realize that here's our system. It's not just interacting with the air around the container, it's interacting with the walls of the container as well. So that there is some loss of energy or loss of heat going to the surroundings. The majority of it goes to the actual air surrounding it. Some of it goes to the actual glass or the container itself. That's why we use styrofoam cups in a calorimetry lab, because it's insulated. You don't lose as much of that heat transfer. The glass, a lot of the heat is lost. But in styrofoam, it's actually insulated, so we get to keep most of that heat. Okay. So we can compare the amount of energy in the system and surroundings during a transfer. So going back to the conservation of energy, any energy gained or lost by the system has to be equal to the amount of energy lost or gained by the surroundings. Much like the roller coaster and the potential and the kinetic energy. If you lose potential energy, you gain kinetic energy. If you gain kinetic energy, you lose potential energy. Okay? If the system loses heat to the surroundings gain heat from the system. Okay? Energy is exchanged between the system and the surroundings either through heat exchange or work being done. So it's an exchange with each other. Your face looked very concerning at that moment. Okay. The internal energy is the sum of the kinetic and the potential energies of all the particles that compose the system. The change in the internal energy of a system only depends on the amount of energy in the system at the beginning and at the end. It doesn't matter what steps we take in between. That's called a state function. It doesn't matter how we get to the end result. It matters what we started with and where we ended. Everything else in the middle does not matter. So that means that the total energy of a reaction is the energy of the products subtracted from the energy of the reactants. Where'd you start? Where'd you end up? Where'd you end up? So let's just say we have a tall mountain. There's two trails, long and winding and short but steep. Regardless of the trail, when you reach the top, you will be 10,000 feet above the base. Okay? So the change in altitude depends only on the difference between the initial and final values, not on the path taken. It's true. Sorry, in New Hampshire, we hiked up a lot and I almost killed my husband. So you've met him. It was a waterfall. We didn't realize how the altitude of the waterfall when we were hiking. And there was a scenic trail and then an easy trail. We went the scenic route. The scenic route was steep, muddy, and we fell down a lot. When we got to the waterfall, there were these families with little kids, baby carriers on their backs marching up. It didn't matter that we took the steep, hard way that was scenic. They took the easy way and they got to the waterfall first.
Because it's easy.
Because it was easier and they weren't like exhausted. By the time we got to the waterfall, we were like, oh God, okay, we made it. So it doesn't matter. The change in altitude only depends on the difference between the initial and final. We all started at the base. We all ended up at the waterfall. It didn't matter how we got there. That really stinks. Okay, sorry. So that is a state function. So here we go. I'm sure you've all heard that when a reaction is exothermic, what is the sign of the reaction? If something is exothermic, what is happening to the heat in the system?
Big smells.
We're losing it, right? Exo, it's going out. If we lose energy, we give it a negative sign because it's a negative system. Energy is flowing out of the system. If energy is flowing into a system, that's an endothermic, and that's going to be positive. Okay? So it's very important that when you're reading these word problems and you're setting them up, the energy going in is going to equal the energy going out, just the opposite direction. So in this case, our positive and negative indicate the direction of the energy flow. Positive means it's endothermic, it's going into the system. Negative means it's exothermic, it's leaving the system and going into the surroundings. So what does that translate to? So here's our system where the total energy is equal to the heat represented by the variable Q and W, which is work. Positive Q means the heat is absorbed. Negative Q means the heat is released by the system. W is the work done on the system. So the total energy of the system depends on the work done and the heat transferred. Okay. It's very important to know that. If you're putting or doing work on the system, it's positive. If the work is being done on the surroundings, it's negative. I'll say that one more time so you can write that down. If the work is being done on the system, it's positive. If the work is being done on the surroundings, it's negative. Can you say it again, or you good? Okay. Very important, because I will say that you're going to get problems where they're going to give you a value for work and they're going to give you a value of heat. And you have to determine the total energy or the change in the internal energy of the system. You need to be able to define or label if the work value is positive or negative and if the heat transferred is positive or negative. That's where you'll get a wrong or right answer. Okay. So here we go. Here's the conventional signs for heat, work, and the internal energy. Okay. So a positive, the system gains the thermal energy. The negative, the system loses. Positive is work is done on the system, and negative means the work is done by the system. So that means overall positive energy flows into the system, a negative energy is flowing out of the system. This is a good chart to study. So heat is the exchange of thermal energy between a system and its surroundings. Heat exchange occurs when a system and surroundings have a different in temperature. Temperature is the measure of the thermal energy within a sample of matter. Heat flows from matter with high temperature to matter of low temperature until both objects reach thermal equilibrium or the same temperature. I said that already. Yay, me. Okay, moving on. Told you I get ahead of myself. So there we go. This is just a picture of what I've already verbally told you, what an endothermic versus an exothermic reaction look like. So Q is negative and the total Q is positive here. So exothermic produces heat, endothermic absorbs the heat. See how it's a lot of the same terminology over and over and over.
So basically, all we have to do is put a plus or minus.
And identify which ones work and which ones heat. Okay. So in an endothermic reaction, the vessel cools, heat's absorbed, energy is added to the system, Q is positive. In an exothermic, the reaction vessel warms, heat is given off, energy is released from the system, Q is negative. Okay. So it's think about when you have a cup of hot cocoa, like today. Okay. Your vessel is going to cool while the air around it, the heat is going to be transferred to the area around the vessel. So your cup is going to get cooler. But when you're heating it up, when you pour the hot water in, then it heats up the vessel. Okay, so the reactor vessel is going to warm because you're actually adding energy within to the cup.
So it'll be initial X and then,
It's always a transfer.
oh,
It's a transfer. Each substance requires a different amount of heat to raise its temperature. Remember the calorie? Okay? So the specific heat capacity of a substance is the amount of heat required to raise the temperature of 1 gram of the substance 1 degree Celsius. That's different than a calorie. Okay? Make sure you know the difference between the specific heat capacity and the calorie. Different definitions. So here's the specific heat of these different elements. So this tells you the amount of heat required to raise the temperature of 1 gram of the substance 1 degree Celsius. So which one is easier to heat of this list? Which one is going to take the least amount of energy to heat? Copper. Who's going to take the longest? Who's going to require the most energy to heat up? Water. Just think about a pot of water that you're boiling on the stove. The pot gets a lot hotter than the water does. Faster, right?
Yep.
Okay. So the formula that you're looking at, because I know that's what you all want to know. It's this one down here. It's the heat. Oh, that stinks. Q, the heat of a system, equals, I write it the mass times the specific heat capacity times the change in the temperature. You see it? Okay. This is our heat. This is our mass. This is our specific heat, our specific heat capacity, and this is the change in temperature. Because remember, it's a transfer, right? So how does this type of word problem look? So calculate the heat absorbed by 15 grams of water to raise its temperature from 20 degrees Celsius to 50 degrees Celsius. So let's write down what our givens are. What do we know? We know the mass is 15.0 grams. We know the change in temperature is going to be final minus initial, so 50 minus 20 equals 30. I looked on here to see what was next. I didn't look on there to check that 50 minus 30 was 20. I just want to clarify. Okay. The specific heat capacity, because it's water, is 4.18 joules per grams degrees Celsius. So we want to make sure our units match, right? So our temperature is in degrees Celsius and our mass is in grams. So we're good. And we're solving for Q. So Q equals the mass, 15.0 grams, times the specific heat capacity, 4.18 joules per grams degrees Celsius, times the change in temperature, 30 degrees Celsius. Multiply it all out, 1,880 joules is the heat absorbed. Is the heat being absorbed or released? What's the sign?
Wait, how did you do it?
Positive, so
Mass times the specific heat times the temperature. It's using this equation.
No, I'm just saying like on the problem it doesn't show 420.
It's in the table on the previous slide.
so
It's a constant, just like R for the universal gas constant, the specific heats. If you're not calculating it, you can look it up. Which leads us to the next part, which is thermal energy transfer or the calorimetry. Ready? Okay, here we go. For this, So if we want to calculate the heat transferred from a metal, we're going to use a process known as calorimetry. Where basically we take two of these equations and set them equal to each other, so it's the flow to one and the flow to the other, so surrounding system. So the idea is the fact that when two objects at different temperatures are placed in contact, heat flows from the material at the higher temperature to the material at the lower temperature. The amount of heat energy lost by the hot material equals the amount of heat gained by the cold material. Basis of your lab activity, that last one, calorimetry. Whatever heat your metal loses is going to be transferred to the water, which is going to gain it. You're going to measure that transfer of heat through temperature. You're going to have to record the temperature change after you add. So you're basically going to take a piece of metal, you heat it up in a beaker of water. So that way you know the temperature of the metal is 100 because the beaker is going to be boiling water. Then you quickly transfer that metal to a beaker of water that's at room temperature or a known temperature, and the temperature of the water is going to change immediately. That temperature changes the amount of heat that's transferred. And then using a bunch of different variables that we have, so that we're going to have the mass of the metal times the specific heat of the metal times the temperature change of the metal is going to be set equal to the mass of the water times the specific heat of the water times the temperature change of the water. And typically what you're trying to find is the specific heat of the metal. Kind of like the gas laws. You're going to have 5 things and you're solving for 1. But you're going to take whatever it is, the 2 substances, and set them equal to each other that are coming in contact. Okay, so here we go. Using this equation. Can you see it all over there? I don't think you can. Here, look, I'll move it. Better? Hopefully. Okay. All right, so a cube of aluminum, initially at 45.8 degrees Celsius, it's submerged into 105.3 grams of water at 15.4 degrees Celsius. So we're talking about, we've got our mass of water, we've got our initial temperature of water, we have our final temperature of water, we have our initial temperature of aluminum. We've got a lot of information going on here. Okay. What is the mass of the aluminum cube? If the specific heat of aluminum is 0.903 and the specific heat of water is 4.18. Well, we're looking for the mass of aluminum. We have the specific heat of aluminum. We know the temperature change of the aluminum. We know the mass of the water, the specific heat of the water, and we know the temperature change of the water. Plug this all in to solve for the mass of aluminum, and you should have 111 grams of aluminum. Gosh, it would be meanest to say then how many moles of aluminum do you have? Thanks, Jason. All right, how do we measure this? Something known as a calorimeter. A calorimeter is a device used to measure the heat absorbed or given off during a chemical reaction. Sometimes they're metal, sometimes they're styrofoam, and I don't know what your college uses. At CCC, we use styrofoam. 2 nested styrofoam cups to reduce the amount of heat being lost to the surroundings. However, what you need to do is when you do a calorimetry, you need to take into account the heat capacity of the calorimeter, because that's also being impacted. It's not just directly the metal onto the water, it's also going to be some of the heat loss by the calorimeter. And that's a constant that you have to actually calculate. Each calorimeter is different. But the calculations are very similar to what we did to the surroundings and the system, or the metal and the water. So let's look at this example. A 0.562 gram sample of carbon is burned in the calorimeter, and the water temperature rises from 25 to 25.89 degrees Celsius. If the heat capacity of the calorimeter is 20.7 kilojoules per degree Celsius, how much heat is generated per mole of graphite? Okay. So we have the Q of the system is going to be the negative Q of the surroundings. The Q of the reaction is going to be equal to the negative Q of the water. The heat of the reaction is going to be the negative calorimeter, heat capacity of the calorimeter, times the change in the temperature. So we're going to have our 20.7 multiplied by the change in the temperature to get our Q. And what units is our Q going to be in? Just by looking at these units. Kilojoules, not joules, right? Watch that, because when you have to put it back into the equation, if everything else is in joules, what do you have to do?
Turn into kilojoules.
No, I would convert to joules first.
Oh.
Yep. Okay. All right. All right. So now, same sample. If the heat capacity of the calorimeter is 20.7, how much heat is generated per mole of graphite, known as the heat of the reaction? Now we're going to take the grams, convert it to moles, and we're going to take the amount of heat and divide it by the moles to get your kilojoules per moles. See, I was setting you up. Did you see how I was doing that? Getting you ready for that mole transfer? Yeah, not going away. All right. Last thing, enthalpy. Are we good with the calorimetry? I know it's a lot of equations. You're given them. You're given these equations. Okay. So that at least helps you a little bit. So that you see now how the first 4 chapters were your foundation. Now we're just kind of applying things to the different calculations. All right, here we go. I'm going to take this away. This is one of the 2 calculations you need to know for the chapter. Hi guys, I know you can't hear me. I mean, I can't hear you, but you can hear me. All right. Is she texting you? I know you were on your phone before. I didn't know if she was saying anything. Okay. What's a state function? Who remembers?
No.
State function. Oh, really?
State function.
It's the mountain.
It's the same when you start, you're at the same ending.
Yeah, it doesn't matter how you get there. It's where you begin, where you end. It doesn't matter which path you take, you're going to end up at the same place. Okay? So, enthalpy is a property of matter that is related to the heat of a reaction at a constant pressure. It's also a state function. It's a mathematical function whose result only depends on the initial and final conditions, not the process used. So here's this fun diagram. So what do you notice about the 2 diagrams that are labeled endothermic and exothermic? Well, look where the reactants are to the products, the amount of energy to go in, and this is energy goes out, right? Exothermic energy is transferred out to the system. Endothermic energy has to be put into the system, right? So this enthalpy measures that transfer. Okay. So delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. Whoa, I skipped. Okay. You might actually like this. So let's say we have this reaction. Now you're going to be given enthalpy values, the heat of reaction. There's all sorts of enthalpy values. There are heats of formation, heats of vaporization, all sorts of little nuances that you get to learn as you move into the next course of study. So, a thermochemical equation is a balanced chemical equation that includes the change in enthalpy for the reaction as it is written, which means that for this reaction, which is a combustion, what do you notice about the enthalpy value? It's negative, which means what about the reaction?
Exo.
It's exothermic, so it's a combustion. Shouldn't it be exothermic? Yeah, you're releasing a large amount of energy to the surroundings. You see the number as well, right? So that you have your products minus the reactants gives you this number. So this isn't just a standard number. I mean, there is a table of them, but you're going to find out where it comes from. How do we know that this specific reaction scheme has this specific enthalpy? So by convention, we calculate the enthalpy change for the number of moles of reactants in the reaction as written. So the enthalpy for 1 mole of the propane is negative 2,044 kilojoules. The reaction for 5 moles of the oxygen is also 2,044 kilojoules. Wherever you are, that's going to be for each of the reactants. So an LP gas tank at a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So we're going to take our kilograms, convert it to grams. Then where are we going to go from grams?
Moles,
And we're going to go to the moles.
kilojoules.
And then we're going to go to our kilojoules. That's how that works. It's part of that whole stoichiometry. Now what happens if it was the oxygen? What would go here? 1 mole of propane, or would it be 5 moles of oxygen? 5 moles of oxygen would go on the top. You're going to take that coefficient down. Here's some important information. When a reaction is multiplied by a factor, the heat of the reaction is also multiplied by that factor. So if you double everything in the reaction, you double the heat of the reaction. If it's reversed, then your delta H is changed. This is leading us to something known as Hess's law. So Hess's law is a way that we write the sum of 2 or more steps to demonstrate or illustrate the enthalpy change for the overall equation. So this is consistent with the fact that enthalpy is a state and it's independent on the steps in between. So we use Hess's law to kind of use all the steps to summarize where it started, where it's going. Okay? So you can use thermochemical equations to calculate delta H for reactions that cannot be done, and calculate delta H from the heats of formation. For example, there is a reaction with magnesium oxide. You get magnesium oxide by burning magnesium. If you do not, you can't put the magnesium strip in the water and burn it. Why not? It's water, it's not flammable, it's not going to work. So you can't calculate the delta H of the magnesium oxide because the process to make the magnesium oxide isn't measured that way because you need the water. You need a liquid or an aqueous solution to measure it by. So we use Hess's law to determine what the heat of the reaction is by going about it a different way that can be measured. It doesn't matter how we get there, we just have to get there. And it sounds a lot more complicated than it is. So suppose I want to know the delta H for this reaction. It's difficult to measure directly because another reaction will occur at the same time, and you're going to get a mixture of the products. But I can simplify it by these two reactions. So we're going to take our original, and we're going to take another step. And then what you can do is you add the two enthalpies to get the total enthalpy for the formation of CO. I want to make sure y'all have it written down. So, if this is the reaction that we're trying to get to, we need to manipulate the given steps, the intermediates that we're using. So that way it looks like this reaction. And we do that by multiplying, dividing, flipping the reaction. So for example, we want 2C in our final product. Where's the only part where we have C graphite in this reaction? Right here, right? Does that have a 2 in front of it?
No.
No, so what do we have to do to make this look like that? You have to multiply it. So that means we have to multiply this whole thing by 2. And if we multiply the reaction by 2, what else do we have to multiply by 2?
The kilojoules.
Yep, the kilojoules. So that also has to get multiplied by 2. Okay. How about this reaction? We have oxygens there, we're good. We have 2CO, 2CO. Do we have to do anything here?
No.
No. So the second reaction's fine. The first one we have to multiply by 2. So remember the net ionic equation where we were canceling things out, and as long as you had the coefficients right, it all worked out? Same concept here for Hess's law. If you change the equations to look like the one that you're trying to get to, the final, things should cancel out so that you're left with just your graphite, your oxygen, and your carbon monoxide. Because our oxygens are going to cancel out. Then you also add your enthalpies to get the total. All right, final example. I know I'm going over, but lab will be short and sweet. I do promise. It's a titration. And it's pretty. No, I know.
What do you
No.
mean short? Like, meaning it's not gonna be like the whole 3 hours, 2, 3 hours?
It's not. It only took the other class 90 minutes.
Okay.
The longest part is prepping your burettes and pipettes, but you already know that process, right?
Mm-hmm.
Soapy water, then distilled water, then you have to rinse it with your you have to rinse the burette with your silver nitrate, and then you have to rinse your pipettes with the sodium chloride solution that you make. So, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, I'll let you work in groups of 3. How about that? Instead of pairs. And then I'll ask that for the viewers at home. We can set this up so that way you guys can at least see just the titration part of the reaction, not the prepping. Unless your group wants you to be around for that boring part. That's up to whoever you decide to communicate with. Okay. Ready?
Yeah.
All right, let's do this. I'm actually going to adjust this over here. All right. So we want to know the enthalpy of the reaction for the reaction of Mo, I can just cover the camera. Okay. For the reaction of calcium metal with water. So this is the reaction that we're trying to get to. That's our goal. And we want to know what our delta H is for that. So it occurs very slowly, so it's impractical to measure it directly, but we have the following information. So what I'm going to do is I'm actually going to mute the screen so that way I can write. And we'll do it this way. Okay? So we have our calcium plus our water makes Ca2 plus 2OH minus plus H2. And we don't know what our delta H is. We know that the reactions are, I turned the page way too soon. You know that the two reactions are H plus OH minus makes H2O. And we have a delta H of negative 55.9 kilojoules. Our second equation is calcium plus 2H plus makes Ca2 plus H2 with a delta H of negative 543.0 kilojoules. So let's see if anything needs to be on the proper side first. And that's it. We have to flip things first. So is our calcium on the reactant side? That looks good. Is our water on the reactant side? No. So we have to flip the reaction. So we have to rewrite it so that way it says H2O makes H plus OH minus, which means that we flip the sign of our delta H. So our delta H,
So
ahead.
it's just plus.
and we make it plus. That's it. I'm making it long and drawn out so that way you guys can see the process. So our delta H would be positive 55.9 kilojoules. All right. I'm going to erase this part. Is that good? You see where it came from? All right, so we're going to flip it. All right, so now we got our water. What about our calcium ion? Is that on the right side? Yep,
Yes.
that's on the
Yes.
right side. Is our H2 on the proper side?
Yes.
Yep. Is our OH on the proper side?
Yes.
Yes. All right, now let's look at the coefficients. Do we have to multiply or divide anything? So calcium doesn't have anything, so we're good. What about our water? What do we have to do to that equation?
Times 2.
So we're going to multiply this by 2. And we're going to multiply this by 2. So this becomes 2H2O makes 2H plus 2OH minus. How's it looking? Remember, we're trying to get to this, right? So let's start combining and canceling out for this. Let's leave the delta H's aside for a moment. So do we have a 2H plus on both sides of the reaction? Yep. Goodbye, goodbye. Okay, what's next? We need 2 waters and a calcium on the reactant side. So we have calcium plus 2H2O. We're almost there. Then we have our calcium 2 plus, which is right there. We have our 2OH plus our H2. Does that match that? And now we can find our delta H. Our delta H is going to be our 55.9 times 2, which is positive 111.8 kilojoules. And to it, we're going to add our negative 543.0 kilojoules. to get a total of negative 431.2 kilojoules. And that's done. The last thing, the very, very final thing. And again, we will go over and practice this mastering chem. There's lots of worksheets, lots of stuff. Final thing for this chapter. Did we all copy it down? The delta H of a reaction is equal to the sum of the mole of the delta H of the formation minus the sum of the reactants. The delta HF of any element is 0, kind of like the oxidation states. Okay. So for example, it looks backwards, but it's good. If we have CH4 plus 4Cl2 makes CCl4 plus 4HCl, what is our delta H going to be? This is delta H of the reaction. Since you can look up the standard enthalpy of formations, they'll generally be given, or a table will be given where you have to apply them. So we know that we have 1 mole, and if you look in your packet, it tells you what the formation of each substance is. Okay. So we've got 1 times negative 74.87 for methane. Chlorine is an element or elemental state, so it's 0. We've got our carbon tetrachloride, which is 1 times the heat of formation of CCl4, which is negative 135.4, plus 4 times negative 92.3. Find the sum of the reactants times the moles, which is what we did. Moles times the heat of formation plus moles and heat of formation. So it's negative 74.87. Those are our reactants. And then the sum of our products. Sorry. Oops. Oh no, we're good, okay. Products. Then the products minus the reactants gives us the heat of the reaction.
That was fun.
Yay, chapter 6 is done. Right? Yes, good, okay.
Maybe we started.
All right. We'll do problems on